if it starts recording. Okay, it seems now it's recording. So welcome everybody. Welcome to this new session of the Severo Seminar course. Today we are pleased to have with us Dr. Marta Liliana Carreño, who's going to talk us about disaster risk assessment. Marta is a young professor at UPC and a researcher at CIMNE. And today this session is kind of special because it falls within the Science Week at Catalonia. So it's a perfect time to have a seminar like this. Well, Marta, Liliana, when you want, we can start.
Thank you, Ignacy. Welcome, everybody.
Welcome.
Let me share my screen. Sorry. Why I can't?
Should you give permissions, maybe? Click on present, then accept permissions or something like that.
Okay.
Yeah, we are now. Yeah, we are now watching your screen.
Perfect. Thank you. So,
welcome.
This seminar will be focused on the disaster risk evaluation. And I would like to start answering some questions. The first one, what is disaster risk here? So disaster risk is defined as the potential occurrence of harmful consequences or losses resulting from the interactions between the natural hazards and vulnerable conditions of exposed elements. Exposed elements can involve, for example, buildings, population, environment, infrastructures, and so on. So why a disaster risk assessment? Why I'm talking about disaster risk assessment? Well, because it is useful to determine what could happen and how likely this occurs in the following future events. The measure is essential to decide because what is not dimensioned cannot be administered. Understanding probable losses due to hazard events creates powerful incentives for countries to develop planning options and tools to cope with risk. So now, in order to do disaster risk management in a proper way, we need to answer some other questions. For example, which are the most and least frequent hazardous events, and which are their severities, for example. Which is the worst possible disaster scenario in a country? How much will be the maximum economic or human losses expected, and with what frequency they will occur? Where can losses be concentrated? Or are possible alternatives for risk mitigation? In order to answer these questions, to do proper disaster risk management, we need to evaluate disaster risk. This evaluation can be done with different approaches. One is a deterministic approach, a deterministic risk assessment, which starts with the definition of a specific scenario, hazard scenario. The damage is represented through expert appraisals and the loss levels are obtained for a scenario with a return period associated. The second approach is the probabilistic approach, the probabilistic disaster risk assessment. In this case, uncertainties are involved in the models. The hazard is represented through a set of stochastic scenarios. Vulnerability functions are used to represent the damage associated with different hazard intensities. And the results are in terms of probabilistic metrics. So in this seminar, I would like to focus on the probabilistic risk assessment. Why? Why this approach? Why this probabilistic analysis? Well, because it is necessary to consider the random nature of the events and their effects. Intensities of the events have a frequency of occurrence, and it is better to express potential losses in rates of occurrence or return periods. The best risk metrics are associated with the exceedance probability of loss levels. And there are uncertainties that must be quantified and propagated through the analysis. So, what is the uncertainty in the catastrophic risk, you can ask? Well, the uncertainty is associated with two causes. The first one, random, due to the lack of data and variability of the case study. And the second one, the epistemic uncertainty, due to the lack of understanding of the processes to be modeled. It's important to say that uncertainty will always be present regardless the assessment scale. So some examples of these uncertainties that I am talking about, we can find uncertainties around the hazard events. For example, when the events occur, how big is the event, where, how is the dynamics of each event, what intensities, or how are amplified by side effects. On the other side, we have uncertainties related to the vulnerability of the exposed elements. For example, how is the response of the exposed elements? What is the capacity of the materials? How is the construction quality? How is the structure damaged? How are the contents damaged? So, the probabilistic modeling identified a set of exposed elements that can be different type of elements that are characterized by some vulnerability conditions, and they are exposed to a hazard, so hazard scenario, and we, with this information, can calculate and estimate the potential losses due to this hazardous event. To these losses calculated will have associated a probabilistic density function, probability density function for the losses. And I can do this exercise for different hazard scenarios. Different hazard scenarios, I calculate the potential losses with a probability density function associated, and so on. Different hazards with different losses, these different hazard scenarios and different losses. And with all the scenarios, the probable scenarios, I finally integrate risk in a probabilistic way. These losses can be in terms of economic losses or human losses. And the main result of a probabilistic analysis is something like this, the loss exceedance curve, which relates, you can see here, the losses with the annual exceedance rate. These results can be in terms of physical damages, economic losses, or human losses, and can be expressed in different metrics. For example, the loss exceedance curve that we just saw, the mean damage ratio, the annual average loss, the pure risk premium, or the problem maximum losses. All of them can be results of this probabilistic risk analysis. At this moment, I would like to tell you about some warnings around the probabilistic modeling. First, we have the most catastrophic events haven't occurred yet. The historical data is scarce. There is short memory for previous disasters, 1 or 2 generations. And we are modeling events with 2,500 years of return period by using information, measured information of the last 30 to 60 years. And very complex phenomena are modeled using relatively simple analytical models. So this modeling, this probabilistic modeling process requires experience and common sense. With these warnings in mind, I would like to share with you this remark. Facts are uncertain, values in dispute, stakes high, and decisions urgent. With this in mind, I can start to talk to you about the process of the probabilistic risk assessment, starting from the hazard evaluation, the probabilistic hazard evaluation. For this case, in the probabilistic modeling, we use a set of stochastic events, a set of possible events. This set of events should be mutually exclusive, collectively exhaustive. They should have probabilistic representation, and all the important historical events should be included. We have to include several intensity measures, statistical moments. We need to have at least the expected intensities and the dispersion grid, and annual occurrence frequency of these events. This is an example of the stochastic events used to analyze the seismic hazard of the Latin American and Caribbean region. All these spots are earthquakes, possible earthquakes in the region, all the possible earthquakes in the region. For this example, for this study, more than 145,000 events are included. Similar representation we may have for different hazards, natural hazards. Here you have 3 examples for tropical cyclones in the upside, and also you have the volcanic ashes and rainfall here. Obviously, we have to use different intensity measures according to the hazard that we are talking about. So here you have some examples. For example, in the case of earthquakes, we are talking about the peak ground acceleration or peak ground velocity or displacement. In the case of hurricane storm surge, we are talking about water depth. And in the case of hurricane rainfall, we are talking about precipitation and so on. With this set of events, we have to calculate an exceedance rate of a measure of intensity. Exceedance rate of an intensity as the sum of these scenarios of the exceedance probability of the intensity, given the occurrence of the scenario, multiplied by the annual frequency of the scenario. With this calculation, I can construct this kind of figure, this curve, which is an intensity exceedance curve for each site of analysis. This curve shows here an intensity measure of the hazard, and here you have the annual exceedance rate. And with this curve, I can, based on this curve for several points of analysis in an area, I can construct different hazard maps, for example, for different return periods, just reading the values in these curves, this type of curves. So this is an example of the seismic hazard for 100 years of return period, or an annual exceedance rate of 0.1. Here you have the example of the hazard map, seismic hazard map for a 500 years of return period and 2,500 years of return period. All this information can be extracted from this type of curves. The next step is the characterization of the exposed elements. So we need to identify and characterize the exposed assets that are susceptible to damage from the hazards. They can be, for example, urban buildings, urban infrastructure, rural buildings, or regional and national infrastructure. Also, the exposed elements can be human occupation, which is a dynamic parameter, because it's not the same if we have an event, a hazardous event at midnight or at midday. So for this characterization, we can use different resolution levels according to the objective of the analysis. For example, we can use a basic level if I am talking about the country and using low resolution proxies. Generally, proxies based on macroeconomic information. I can use also a medium level resolution if we are at subnational level, also using proxies, also based on macroeconomic indicators or demographic information or infrastructure information. And finally, we have the detailed level of resolution used for urban areas when I have building by building information. This is an example of the resolution level used for the Global Assessment Report of UNDRR in 2017. And in this example, some areas were defined, and using the capital stock, they were evaluated, and you can identify the main cities in Spain here. Other example of resolution level is this one for a subnational level in Colombia, province by province. Or a detailed level used here for the city of Lorca, where the replacement cost building by building was estimated. In the case of urban areas, according to the available information, also we can use different levels of resolution. And the exposed elements should be related, the vulnerability of the exposed elements should be identified. And when I am talking about vulnerability, I have to say that vulnerability has different dimensions. We can talk about physical vulnerability, economical, financial, social, environmental, cultural, ideological, politics, institutional, and educational dimensions of vulnerability. But in this seminar, I will focus on the first one, the physical vulnerability. But in order, if I need to understand in a holistic way, in an integral way, the problem of disaster risk, I have to include also other dimensions of vulnerability. In the case of physical vulnerability, we use vulnerability functions like this one, where here you have the relationship between the intensity of the hazard and the damage for a type of element, of exposed element. And for these vulnerability functions, we use the mean value and a standard deviation. These are examples of vulnerability functions for earthquakes in the case of buildings with different structural typology with a seismic design level moderate. You have here unreinforced masonry, reinforced concrete frames, steel frames and shear walls. And here you have the mean values of each vulnerability function and the standard deviation, the variance. In the case of wind, you have here the intensity measure for, in the case of wind, is the wind speed. And here you have the mean damage ratio. And here you have the vulnerability functions for different typologies: wood frames, reinforced masonry, and reinforced concrete frames. With all this information identified, I can now evaluate the disaster risk. So I need to evaluate the losses for a city, for example, due to different scenarios, different hazard scenarios, hazard events. So I can do the evaluation of the potential losses, all the possible losses, and all of these losses will have associated a probability density function. And I can I can know what is the probability of exceedance of different levels of losses. To do this, it is necessary to obtain the probability distribution of the losses for each event. That is this. But this, in general, is not possible to do it directly, so we use two conditional probability distributions that you can see here. The first one, the probability to have a level of losses due to an intensity, which is related with the vulnerability of the elements, the exposed elements. And the second one, the probability to have an intensity due to given to the occurrence of an event, which is a component related to the hazard. So we need to do the evaluation, the calculation of the exceedance rate of a level of losses as this, the sum of the probability of exceedance, this level of losses divided by the time. Or, well, the same, compute the sum of this exceedance probability of the level of losses multiplied by the annual frequency. You see this in a more clear way. You can here you can see a kind of flow chart for this probabilistic risk modeling. So the first step is the select an event from the set of events, the stochastic set of events. Second, we need to select a site in the study area. If I have a grid, I will have several points to evaluate. Select the construction type or the type of exposed elements that I am talking in this site, and identify which is the vulnerability function for this kind of elements, where I can identify the intensity of the event at this site and calculate the loss for this event. Now, there are other constructive types in this area. If yes, I have to repeat this process for all the construction types in this area. If not, I can ask now, all the study area, I have analyzed all the area. If not, I can repeat again these steps, or if I finish all the area, I can calculate the probability density function of the loss for the event. Now, all the events were analyzed. If not, I have to do all this process for each of the events in our stochastic in our set of stochastic events? If yes, I can do the integration, the risk integration of my results for all the scenarios in a loss exceedance curve. And this can be done with the integral of all these probability density functions for each scenario and construct like this the loss exceedance curve. I have the loss here and the loss exceedance rate, the annual exceedance rate. This can be calculated, as you can see here, as the sum of for all events of the probability of the exceedance of a level of losses given an event multiplied by the annual frequency of this event. With this kind of analysis, with this kind of result with the loss exceedance curve, I can do a risk stratification. What is that? I can define different layers. For example, a layer with high probability and low to moderate losses here, or a layer with medium probability and moderate to high losses, another layer with low probability and high losses, and very low probability and very high losses. With these layers, I can also identify in which cases I can face or I can reduce these losses using planning, prevention, and mitigation measures. I can also identify in which cases I can apply regulations, for example, codes, standards, or land use planning, and which amount of losses can be avoided like this, can to be faced with these measures. Also, I can define warning systems or emergency response measures. This kind of result also is useful to design a financial instrument, to cover the losses, the potential losses. For example, define which kind of losses can I face with my own budget, or taking a contingent credit, which amount of losses I can transfer through insurance and reinsurance, or what kind of losses I can't avoid with all these instruments. Other result of this kind of analysis is the average annual loss. It represents the amount that has to be paid annually in order to cover future expected losses. This, you can see this more clearly if you see here in this figure, the green bars correspond to the losses for different events. This is time, and at this side we have the losses as a percentage for each event in these green bars. At this side, at the right side, we have the accumulated losses, which is this red curve. If I have the accumulated losses, I can draw this kind of thing. And when I find the strength of this red figure, I have something like this, where the slope of this line corresponds to the average annual loss, which is the amount to pay annually all the potential future losses. This can be calculated with the base of our events as the sum for all events of the expected loss given an event, the occurrence of an event, multiplied by the annual frequency of the event. This metric, the average annual loss, is a compact probabilistic metric, and it is relatively insensitive to uncertainty. And this metric can be obtained to represent risk for a building, a set of buildings, a city, or a country. This is an example of the results. This is the case of Lorca, in the case of earthquakes. And you have here represented the average annual loss, building by building, for Lorca. Here you have the same result, but now as a relative value relative to the replacement value defined at the beginning. And this result now in a relative value is named also the pure risk premium. Somebody can think now in insurance. Well, this is related to the insurance. Sorry. Another kind of result that we can find in this analysis is the probable maximum loss. I can read directly from the loss exceedance curve, which is the probable maximum loss for different return periods. Now I'm talking about the return period of the losses, not the hazardous events. So here you have the losses and the annual exceedance rate, and you can read directly the losses for different return period. Calculating the return period based on the annual exceedance rate. With this kind of analysis, we can identify risk management alternatives. If this is my current risk calculated, I can define a resilience target. I can say, okay, I will do this risk reduction. How? How can I do that? Well, I can identify structural measures, for example, the adoption of standards for new infrastructure investments, for example, or engineering assessments to retrofit critical infrastructure. This will reduce direct losses. We can also define financial instruments. For example, I can do the estimation of the cost of risk transfers, and this will reduce the net loss and accelerates the recovery. Also, you can define response plans, contingency plans, or early warning systems And with this, we'll improve the system performance and reduce the indirect losses. This is an example of the results of the average annual loss. This is the case also at the global level of the Global Assessment Report on Disaster Risk Reduction of United Nations. You have here the results of the average annual loss, and here you have the same result, but in relative values, relative to the capital stock of each country. So now I would like to have have some comments around the probabilistic models that you have seen here. The first one, the use of catastrophic risk models has increased in the last 45 years. And these models are used by the insurance and reinsurance industries. And the main objective of this kind of analysis is to give orders of magnitude of the losses associated with natural events, but orders of magnitude of the losses. Somebody can say this: all models are wrong, but some are useful. And finally, the limitations should not be understood as errors, but the results should be understood in a context. Finally, a couple of conclusions. Well, considering uncertainties does not increase the precision of a model, it increases its transparency. And also, understanding probable losses due to potential hazard events creates powerful incentives for countries to develop planning options and tools to cope with risk, including the budget allocation necessary to reduce the potential damage and safeguard the transformation of development. Now, just to finish, I would like to leave you this remark attributed to Winston Churchill. I think that is very good for this base. Never let a good crisis go to waste. And well, that's all. Thank you for your kind attention.
Thank you very much, Liliana. We have time for some questions. If somebody wants to ask something, you can open the mic or write through the chat. Well, if nobody wants to ask, I had one curiosity, Liliana. You were talking before about how to measure the physical vulnerability.
Mm-hmm.
And you said that there are other kinds of vulnerabilities, which are also important. And I was wondering, how can you measure social vulnerability or cultural vulnerability? Do you know any way to do that, or?
Indicators. Usually, they are measured using indicators, different kinds of indicators.
But is it common to evaluate all these dimensions?
Yes. There are normally the vulnerabilities evaluated by different disciplines, different areas of knowledge, but it's necessary to involve all of them to have a real view of risk, because you only with the physical part have not the whole picture of the problem. Mm-hmm.
And I guess that for insurances, they also account for all this other, let's say, dimensions.
Yes.
Okay. Thank you. Is there any other question or comment?
Yeah, please, Liliana. I'm Cecilia. Congratulations for the seminar. It was very interesting, especially for us, for the ones who didn't know much about this issue. I wonder, for all these analyses that you take, that you are making, it's easy to find all the data to conduct those studies.
Not always is easy. The main problem is to find the data.
Yeah, I guess. It's all. So but I guess that lately, no, with all these new elements like drones and IoT and all the kinds of ways of getting data, there will be a revolution, no, in this kind of models, probably in the next years.
It depends on what do you want with the analysis, because not always drones have all the details or the information that we need. Depends on what do you want.
Okay, so I guess that the message probably is better to have less data but very precise than a lot of very noisy data, probably, no?
Yeah.
Okay. Thank you.
Okay, thank you. Is there any other question? If there are no more questions, let's close this seminar like this. Thank you very much again, Liliana, for this nice presentation.
Thank you.
And I hope to see you all in the next session in 2 weeks. See you.
Bye.
Thank you. Bye-bye.
Bye.